Okay, thank you so much for inviting me. Thank you, Jen. Thank you, the EPRV RCN team. And yeah, I'm Baptiste. I'm a postdoc at the University of Oxford, and I'm absolutely delighted to be here with you today to try to kind of give you a glimpse of what wavelength domain-based method can help us with activity modeling in the search for Earth twins. And so that's basically the overview of my talk. So I will start by a brief context that basically everyone here knows, but at least we'll be on the same page. And then I will have a glimpse to time domain modeling methods, in particular Gaussian processes, but I will focus on the limitations of these frameworks for the search for long period low mass planets. Then I will see how wavelength domain-based method can help us using kind of two approaches, one more data-driven, linked to scalpels and this method when you try to build a basis and project your radial velocity on, and a method that is completely bypassing the RV, which is Doppler imaging, on which I've recently made progress. So that's kind of the overview today. And let's get started with the context. So in terms of context, you all know this plot is probably one of the best way to represent the effect on activity on RV planet search. So this represents all the planets detected by the radial velocity method as a function of the year of discovery. So you have the semi-amplitude in the y-axis, and the little stars here indicate some of the iconic instruments currently in operation and their radial velocity precision. So this plot is inspired by Anna John, who in the audience as well, was working in St. Andrews and now in Birmingham. So what you see is that from maybe until 2010, we were able to detect less and less massive planets, which reflect the fact that instruments were being more and more precise. And now that we reached the 30, 50 centimeter per second precision, we're definitely limited by stellar signals and in particular by stellar activity. So now with upcoming projects, now we have the PLATO mission, the ESA PLATO mission in 2026. We'll have the HARPS-3 and the Terra HuntingExperiment starting soon, and KPF as well. We are going to address this activity problem because this is our main limitation now to search for long period Earth mass planets around Sun-like stars. And that's really what I will focus on during this talk. Okay, a brief reminder of the different signals that we are seeing that are due to the star itself. Here, so in blue, I write what could be like linked to photospheric flow. So we have oscillation, granulation, also super granulation that we still don't really understand. And there is a lot of work going on at the moment to try to characterize it and maybe filter it if we can. There are other circulations issues that are barely mentioned and that I will not talk about, like the Evershed flows around stellar spots, meridional circulations as well. And what I put in red are the effects linked to magnetic activity, so flares on relatively short time scale. And what will interest me today is mostly the signals that are due to spot and faculae and magnetic cycles. So this is really what I will tackle today. So supergranulation, I will not talk about that because I don't know how to filter it, but I will talk on the right and two effects here. Okay, and in particular, what I'm going to try to handle today is the effect caused by what we call the contrast effect, which are mostly affected by spots. So this is just due to the fact that when a spot crosses the stellar disk, it will occult the blue shifted hemisphere of the star, and then will travel and occult the red shifted hemisphere. So this distorts your stellar absorption line and modify the center of gravity of this line, then therefore modify your RV content. So this contrast effect is more dominant for spot-dominated stars, so would be mostly like active M dwarfs and pre-main sequence stars. And this effect is chromatic and decreases with the wavelengths and being quite small in the near-infrared. I will not really talk about near-infrared follow-ups today. I will really focus on sun-like stars. But in the near-infrared, you're also sensitive to the Zeeman effect. So it's not because you're going in the near-infrared that it's easier to find your planets. On the other hand, for stars like our sun, we are sensitive to another effect linked to active regions, which is the suppression of the convective blue shift. Brief reminder is that because upwards going granules at the surface of the sun carry more flux than downwards going granules, we have a natural blue shift of the disk-integrated spectral line. So within an active region, and in particular within an active region that has quite a small contrast with respect to the photosphere, like faculae, will locally suppress the convection, and the local line profile will not have this convective blue shift. So when you take the disintegrated line, you will see a distortion in your line profile. So this effect is dominant for the sun and dominant for probably F and G stars, maybe K stars as well. And it has been shown that it is also stronger for a shallower line because these lines are formed deeper in the convective zone and therefore are more affected by convective effect. So these are kind of the two effects that are linked to active regions that I will try to describe today. Okay, and a good way to, to just test or assess our activity modeling framework perform is to look at the sun as a star. And today I will really focus on observations collected with the HARPS-N high resolution spectrograph at La Palma since 2015. So this data until 2018 is public, and the rest of the data will soon be made public by Xavier. What you see here is all the data after a pre-selection. So you need to just make sure that there is no cloud obstructing part of the sun, because that will act like a spot. You also need to make sure that the air mass difference between one end and the other end of the sun is as small as possible. So we make all this data selection. Then we also pre-process the data using Michael Cretinier's Yarara code that is working very well for the sun. Another interest of the sun is that there is no planet. I mean, at least we can remove all the planet signature from the solar system planets. So we end up with a radial velocity signal that you see here on top that contains mostly stellar activity. The photon noise is very low. This is daily average data. So the photon noise is probably 0.1, 0.15 meter per second. That's really low. You do have a long-term instrument stability of 0.4, 0.5 meter per second as well. So what you see is mostly due to stellar activity. And you also see clearly the cycle effect here, or you can go just here. So you can separate this data set into kind of three parts. The first one will be the end of cycle, the magnetic cycle 24. Then you reach a long solar minimum. And then you start with cycle 25 with a more active sun than before. Just also to describe it, here we have the FWHM of the cross-correlation function, the bisector velocity span, so the BIS indicator, and then you have the S and X here. The cut here is just due that there was operation on the instruments, and so that felt quite natural to just have a cut here for this period here. So that's our input data set. It's just worth mentioning that other instruments like HARPS, Express, NIRID are observing also the sun. And I will invite you to this paper from Lili Zhao that compares our ability to probe solar signal whilst observing simultaneously with different instruments. I see something in the chat, or is everything fine? Okay. I'm assuming that you can still hear me.
Yeah, you're all set, Baptiste. Mikael was commenting on the spelling of Yarara.
Sorry. Oh. Okay. So now that I set up our framework, I will try to model stellar activity. And the way that will traditionally go, if you get your radial velocity signal here, you will model it with a simple model containing a planet signature, a stellar activity contribution, and a white noise term. Okay, that's as simple as we can get. And stellar activity is always tricky to model. The way we will do that in the time domain is to model it as a Gaussian process. So when you model your stellar activity with a Gaussian process, you say that your stellar activity signal is drawn from a stochastic process. And in particular here, it's a multivariate Gaussian. The trick here is just to say that, yes, my signal is drawn from multivariate Gaussian, but I can parameterize the covariance kernel, so the correlation between each pair of data points in my signal. And there are many different covariance kernels that can be used. The most popular one to model stellar activity is this quasi-periodic shape, which just makes sense because you expect your stellar activity radial velocity signal to be periodic because the star rotates, and your active region will evolve, and so you have this quasi term that is the exponential decay. So typically our kernel will be using three parameters, which will be the period of your Gaussian process that match the period of the star, the decay time of the spots of the active region, and the smoothing that just controls the width of your peak, and that controls how smooth your signal will be. So if you have a very large smoothing, that means that you cannot fit anything. You will have kind of a straight line, a very slowly evolving signal. And if your smoothing is very small, then that means that you will overfit your data because you can fit everything. Okay, so what we're going to do is we're going just to assess our ability to model this radial velocity signal of the sun. And we're going to do that in 3 separate chunks. So we separate our data into 3 chunks, and we will model each chunk separately. 1 chunk in the end of cycle 24, 1 chunk in the solar minimum, and 1 chunk in the start of cycle 25. For each chunk, I use the same time span, the same number of epochs, and about the same sampling, which is 1 point per day. Okay, we model this signal without any planet because we're interested only in activity so far. And this is what we get. So this is the posterior distributions that you get on the 3 parameters of the Gaussian process. So on the blue field blue region, you have what we get on the end of the cycle 24. The solar minimum that quite follow the start of cycle 25 are in red and yellow here. The first point I want to mention is that, yeah, we do have a variation of the hyperparameters. And the interesting part is that we know where this variation is coming from. If you look at the rotation period here, you have a 2 sigma difference between cycle 24 and 25. And this just reflects the fact that you have differential rotation at the surface of the sun. So at the end of the cycle, the active regions are closer to the equator, and they rotate faster. And at the start of the cycle, the active regions are formed at higher latitude and rotate slower. It's quite similar with the time decay. Just translate the fact that the sun is actually more active when it starts at cycle 25. So stronger activity means a longer evolving time. Also, the smoothing parameter is quite different as well. And this is probably because when the active regions are going in the equator, they create a more abrupt change in the radial velocity signal. More abrupt change means less smooth signal. And that explains why we are less smooth in the end of cycle 24. Last point is that the fit is quite good. Actually, we remove all the quasi-periodic variations, and we have a residuals of 0.6 meter per second, so much larger the photon noise. That just translates the fact that we haven't filtered supergranulation. There is probably also some instrument stability accounted for this amplitude of residuals here. Okay, so we notice that the hyperparameters are varying over the cycle. And then we can try to probe that a bit more by, instead of modeling that into 3 chunks, by modeling all solar data into 10 rotation period long chunks, and just sliding a window to see and to try to explain better all our hyperparameter change. And what we find when we do this test is that we have quite a large variations of the hyperparameters with the magnetic cycle. The most dramatic parameter variation is with this smoothing parameter that I told you before is very important for our GP modeling. The smoothing of the GP correlates very well with the whole spot area or the filling factor of the active regions at the sun's surface. The way we can understand that is that if you have a lot of spots at your solar surface, that means that the signal will be more smooth because you will not have suddenly a large group of spots arriving and then breaking your radial velocity signal. Whereas if you are less spots on the stellar surface, you're more likely to have suddenly a latitude with quite a lot of spots there that will create an abrupt variation in your radial velocity signal. The problem with that is, since the hyperparameters are varying so much, that means that if you're going to model your full radial velocity with a Gaussian process, you will end up having a poor fit with a typical RMS in the residuals of 1.2, 1.3 meter per second, which is definitely not what we want in the search for 0.3 and even lower meter per second planet signature. So our GPs perform well with quasi-periodic signals, but not really with magnetic cycles. That's the take-home message on the time domain filtering. So there are many ways to try to tackle that, and the way I want to talk to you about today is just trying to use wavelength domain information to handle this issue. And I give you a little overview of some of the wavelength domain method that's been developed in the past, let's say mostly past 5 years. And I classified them as what I call RV bypassiveness, which is just how much information in your spectra you use, and will you use it on the RV or not. The first type of philosophy is just saying, I'm going to continue model my signal with a GP, but I will use other indicators that I derive, for example, from the spectra, so chromospheric emission, magnetic field, and you are going to inject that into a multidimensional Gaussian process. So we're still very close to the RV. Then we can go a bit further and saying, okay, I will use my spectrum, and I will define a basis that is absolutely insensitive to the activity, and that will just leave my planetary signature with much less noise than when there is activity. So trying to filter just by a projection of the RV. Then the method that is becoming increasingly popular is line-by-line RVs, trying to, now that we have spectra that are that precise, you can absolutely have a decently precise RV on the line level. So this gives you, for each spectrum, thousands of radial velocities, and then you can use dimensional reduction techniques to filter some part of the activity. You also can identify some generic variation in your RV, typically the temperature dependency, that can help you to filter your RV in a more physically realistic approach. And finally, you can say, oh, no, I don't want to work with RV. I'm going to model the full line profile or the full spectrum. And that's notably what I will talk about in the end with Doppler imaging. So today, I'm going to focus on two methods that are quite representative to what we can do. And that's quite at the opposite of the spectrum between data-driven approach, where we don't really inject a lot of physics in the data, and a model where we absolutely want to model the activity within the spectrum itself. Okay, so the first method, I'm sure that you're all familiar with that because that's Andrew's favorite method, scalpels. The goal of this method is just saying, if you have a planet signature on your spectrum, it just induces a shift, a pure shift in your stellar lines. So that means that if you take one spectrum as a reference, like the average of your spectrum, for example, and then if you subtract this spectrum from any observation you have, what you will have is a signature that depends only on the first derivative of your spectrum with respect to the wavelength, or the CCF here. Inversely, if you now consider stellar activity, they will not induce a shift, but they will distort the stellar lines. So that means that you affect the shape of the line, and therefore you affect the derivative of order 2 or more of the lines. So in other words, if you're able to separate your spectra into pure Doppler shifts, which are affecting only the first derivative of your spectrum, and everything else that is affecting all higher order derivative, you can filter stellar activity, and then you can get only your planet signature and other kind of residuals that you can have that will induce shifts in your spectrum. How do you separate your spectra? There are different approaches. Scalpels using the autocorrelation functions because it's independent from the shifts. Here in the approach I'm going to present here, which has been introduced by Jones et al. In 2017, we just use a Taylor expansion of your spectrum of the spectrum with respect to the wavelengths. That gives you a first term that is associated to the first derivative of the spectrum, and that will contain all the planet signature that you want. And then the other term will be all associated with distortion of the profile and therefore associated with activity. So the way we'll do that is we'll do a Taylor expansion of the spectrum and then get Doppler shift and shape distortion. From the shape distortion that is planet independent, we're just going to build a basis using principal component analysis. And then we get a basis that is only sensitive to activity-induced variations. What we can now do is project all radial velocities on this orthogonal basis. That will give us a radial velocity time series that is only dependent on stellar activity. And then we can subtract this activity-only radial velocities from the rho RVs, which will give us the planets or like the shift RVs that are just sensitive to planets and shifts in the spectrum. So this is validated on simulations. And how does it perform on the sun? So if I get back to the solar RV observed with HARPS-N, you have here the rho RVs. Here on blue in the middle, you have the activity corrected RVs using this framework. You see that we reduce the RMS by a factor 2 almost. And here you have the shape-driven, so the activity RVs that capture very well the cycle-induced variations here. You really feel it, whereas you don't see it at all in the shape-driven RVs. So that's a great trend. Now we are able to filter stellar activity, cycle-induced variation. Okay, but now are we able to filter very well quasi-periodic variation? So let's take a periodogram of this activity-corrected RV. And this is what we see. So this is a periodogram, and you see that we see that we have a peak at the rotation period of the sun and the first harmonic. The way I understand that is probably because you have crosstalks. Your third derivative can look a little bit than the first derivative, and so you cannot eliminate every bit of activity in the shift-driven radial velocities. Yet we were able to filter very well the magnetic cycles effect. So we need to go further, and I really redirect you towards Aushan's use. So he's a PhD student in Oxford, and he's done a paper when he used a Gaussian process, not to model radial velocity, but directly to model every bin of the CCFs. And that works pretty well. So that's really a paper I encourage you to read if you haven't come across that. If I do a little temporary summary for this data-driven method, this method is ultra fast and it's absolutely independent from the sampling that you use. So it can be a very good way to filter stellar activity when you don't have a very good sampling of your signal. But on the other hand, you know that we're not filtering everything. So that's just the problem to keep in mind. It hasn't been tried a lot on very different spectral types yet, like M dwarfs, pre-main sequence stars, and it's really worth trying. And also it's worth trying that on different wavelengths, typically in the near infrared. That could be very interesting. Okay, so for the last bit of the talk, I'll be talking about a method I've been working on quite a long time now, and it's finally giving results. So I'm very excited to show you what I got. So Doppler imaging is a method that's been inspired from medical imaging, and that's been around for decades, literally decades, for modeling the stellar activity on very active stars. So I give you a little glimpse on all the papers that, I mean, not all, like some of the papers that you can find about Doppler imaging. What we do in Doppler imaging is we want to model, instead of modeling the radial velocity, we're going to model the full spectrum. Or in this case, I will model the full CCF for computational reason, but it can be extended to the full spectrum if we want. Okay, the principle of this method is that you have a time series of CCF here. So obviously our CCF don't look that distorted, but this is just for the example. This is data of a very young star here. And the goal of Doppler imaging will be to invert this time series of CCF into a distribution of active regions at the stellar surface. So our model is physically driven. We really want to recover where the active regions are at the stellar surface. So what you can do is you can generate spectra from a stellar map like that. You divide that into a lot of grids, and from each grid, you can compute a local spectrum that you weight depending on the limb darkening, the visibility of the cell, the inclination of the star, and the local brightness. So what you can do is to generate a time series of profiles, what I just said, at the different epochs of observation. And so obviously, in this case, the brightness of my star is supposed to be 1 everywhere. And so we don't match our observations. And we are going to change and to optimize the brightness distribution of the star until the observed profiles are matched by the observation to a chi-square of typically matching the error bar. And obviously, this problem is ill-posed. That means that it's super degenerate. We have an infinite number of maps that can reproduce as well the profiles. So we need to add a regularization condition. And the typical regularization that I will use today is called the maximum entropy solution. It means that we take the only solution that matches the profile at chi-square equal 1, and that has the least information on it. So it's just the maximum entropy information. And what I say information, that means like the spot coverage overall on my surface. Okay, so as I told you, this method works well when the stars rotate fast, and it's not been applied to sun-like stars because there are some problems there. And I'm going to just talk about that briefly. When the star is very active, it generally means that the star rotates relatively fast. And when you have a fast rotator, you do have a quite good resolution on your line profile, because you see that if you have a big distortion there, you can associate that to a location of a spot at the stellar surface. When you have a fast rotating star, you can also constrain the differential rotation via if you have like enough observation on consecutive observations. On the sun is a slow rotator with a V sin R of 2 kilometers per second. So you quite lose this spatial resolution. But on the other hand, now we have extremely precise spectra. HARPS-N solar spectra are super precise. And not only we have precise spectra so that we can resolve the active regions effect, but we can also follow them in time because we have a good time sampling. So these two problems still allow us to apply Doppler imaging to slow rotators like the sun. The second problem that we face is that the solar activity evolves very fast, typically on the order of 1 rotation period. And that means that the sun does not really look alike after 1 rotation. So if I use just traditional Doppler imaging frameworks, the evolution of stellar activity is not included there. So what I'm going to do is I'm going to divide my solar data into chunks of 1 rotation period. And I'm just discarding the chunks when there is not enough points. I'm going to apply Doppler imaging independently on these 23 chunks of data. I'm doing completely independently. And ta-da, this is my result that I got from the sun. So this is the sun reconstructing from spectra only. I know what you're thinking. Oh, well, that does not look like the sun. Yes, because even if we can apply Doppler imaging, we are, as I said, like still resolution limited by the fact that the sun is a slow rotator. But I see that we are able to reach spatial resolution of typically 18 degrees, corresponding to spherical harmonic of degree 5 at the surface of the sun. So these are our outputs. So I'm only showing here the phase corresponding to the first observation of each chunk here. The first question we want to ask here is, okay, we got maps of the solar surface. So can we compare them with actual observation of the sun? That's now what I did here. So I compared them with SDO observations of the sun, and I took the first map here. So obviously you cannot directly compare them. So I did a low resolution image of the SDO spectrograph, SDO Dopplergram by modeling this image by spherical harmonic of degree 5 here. And I took the Dopplergram. I also tried the magnetogram. We don't have a great match with the magnetogram. We don't have a great match with the intensitygram, but we do have a good match with the Dopplergram, which is linked to the fact that in a star like the sun, we are mostly sensitive to variation in the velocity field of the solar surface. So I saw this first map, and I was like, oh, wow, that's matching pretty well at low resolution. I must say, like, wow. And then I looked at other maps, and no, I was not matching at all. And I was really triggered by that. I was, is it just a coincidence that it works for some phase and not for other phases? And I thought, it took me days, weeks. And then I realized something is that I was plotting all my comparison at the same phase, which is a random phase, what I call rotational phase 0. But there is one point to consider, is that Doppler imaging won't be performing very well if you don't have any radial velocity information. If your radial velocity of a given phase is 0, that means that you don't have much to model on your sun. And on the other hand, if I have quite a large value of the radial velocity, that means that you will have a proper distortion on your spectrum. And that means that you can definitely put an active region there. And so what I did is I took all my maps at the same phase, and I compared here on the x-axis, you have the correlation between the Doppler imaging map and the SDO map. And on the y-axis, you have the radial velocity at the phase where I compare the two maps. So you see that when the absolute value of the radial velocity is high, we tend to have a better correlation with the SDO map. And that was expected. That's basically the reason why we didn't have a match on the other two. So what we can now do is saying, for each chunk of data, I'm going to take the radial velocity, the maximum absolute value of the radial velocity, and now I'm going to compare the maps at the phase that maximize this absolute value of radial velocity. And so that's my phase before, that's my comparison before, and once we take that, that's what we get. So we do get a much better match. Obviously, it's not identical because we do have variations linked to different effects on SDO, and Doppler imaging is definitely not perfect, but at least it tells us that, okay, we are reconstructing something that is not completely off. And that is good just as a check, I would say. What interests me today is our ability to filter stellar activity with Doppler imaging now. So another test we can do is we can say, yeah, we have our maps, and from our best fitting maps, we can compute line profiles here. Oops. And from these line profiles, we can compute a radial velocity here. And then what you see here is the radial velocity computed from our Doppler imaging maps, superimposed to the HARPS-N radial velocity. And you see that we get a RMS of 0.6 meters per second, which is absolutely comparable to what we got when we modeled stellar activity signal with Gaussian processes. Okay, so if I go a bit further, we can also take the periodogram of these residuals. And what you see is that on the bottom, you have the residuals, and we have filtered very well the quasi-periodic signal that was due to activity. So that's a good news. Okay, the last bit I want to talk about is now, okay, you've shown that Doppler imaging performs relatively well at filtering stellar activity. How about finding planets? And that's really the point that matters. And that's why I conducted a planet injection recovery test. And that will be the last bit of my talks here. So I conducted two kinds of tests. And this is the first one. The first one, I'm saying, okay, I'm injecting planets in the CCFs. And then I'm going to apply Doppler imaging blindly, regardless of whether there is a planet or not. And this test will just test how good is Doppler imaging to just detect planets from a given radial velocity time series of spectrum. I injected 3 planets, so the first one is I would say on the easier side, and so 2 short period planets, and then 1 long period planet with relatively small semi-amplitudes. And you see that in every case, the largest peak in the residuals correspond to the injected planet. Okay, good point. So what I now do is I model the residuals, searching for this planet signature. And what I found is that the recovered semi-amplitude is systematically underestimated, and by quite a lot, by at least 40%. So the result is that, yeah, Doppler imaging seems to work pretty well to find the planet, like the orbital period and phase, but not really with the semi-amplitude, because part of the signal is probably absorbed by the Doppler imaging process. Yet, if we do that like that, we can just see how good our Doppler imaging performs as a planet detection tool by doing just blind planet injection recovery tests. So I injected like now 1,000 of planets in the CCFs that I have as an input. And I just say my detection criterion is I will compare different methods to filter activity. a simple sine wave fit at the rotation period of the sun and harmonics. The method I was talking before, which is the wavelength domain-based data-driven approach, and the Doppler imaging framework. In each case, I filter stellar activity blindly from the input radial velocity. And then from the residuals, I say, what is the largest peak in the periodogram? And does this peak match the injected period of the planet? And do we have a good false alarm probability or a small false alarm probability for that? And you see that in the first case, when we have the oversimplistic model for stellar activity, we lose sensitivity as we decrease the semi-amplitude of the planet, which just makes sense. In the DCPCA, we do perform much, much better for planets until the 0.4-ish meter per second level of injected planet. And we kind of lose a little bit of sensitivity to smaller long planet period. Then if you go in Doppler imaging, we perform exceptionally bad when the orbital period of the planet is relatively close to the rotation period of the sun, which is fully expected because our method is needs the spectra to be rotationally modulated. So yeah, if you have a planet that is at the same orbital period, it doesn't work. On the other hand, we do perform quite surprisingly well to search for long period low mass planets. So that's good to know that at least we are sampling a range of orbital period and semi-amplitudes that is quite unsampled by other methods. So that's a good ancillary method to find long period planets, at least from this test. Finally, and that will be the last point of my talk. So you remember that what I said is we applying blindly Doppler imaging to our spectra, we will absorb part of the planet. So if we want now to accurately determine the semi-amplitude of the planet, we need to jointly apply Doppler imaging and planet fit to our spectra. And we're going to do so using this method. So we have our observations here, and I'm assuming that there is a planet signature there. So what we're going to do is we're going to build a grid of planet parameters here, orbital period and phase and semi-amplitude. And for each set of parameters in the grid, I'm going to correct for the planet signature. So I'm correcting only for the wavelengths because I don't want to interpolate my CCFs. And then I'm going to apply Doppler imaging at fixed level of information, which will give me a chi-square. So in the end, I will have a chi-square map. And from this chi-square map, I can determine the best fitting parameters. And I can also do that for every chunk that I have. That will give me different estimates of the planet orbital parameters. And I can just combine them in the end and get my best fit parameters. And this is what we get. So this is the last two planets that I showed you before, the short period planet with a semi-amplitude of 0.4 meter per second, and the longer period planet with 0.5 meter per second. And you see that compared to state-of-the-art GPs, we perform pretty similar with our model that does not account for stellar activity evolution. And so basically, I would say that this is promising. That means that maybe Doppler imaging as a proof of concept can work, even with traditional frameworks. And I will push towards making a more operational version of the code, a maintained version that could be shared to the community. And that's my take-home message for Doppler imaging, is that now everything I presented will soon be submitted for publication. And there are no ways that we can go to make the code faster. We can move this code hopefully to the Bayesian framework instead of just doing a chi-square fit that will be much more robust. We need at some point to consider how activity evolution can be included, probably with coupling our Doppler imaging framework with Gaussian processes, for example, and maybe trying to account better for like trying to add physics in what we are reconstructing. Typically, rather than modeling the brightness, modeling the velocity field, that would be interesting. And that's my conclusion. So of this talk. So I just say, yes, there is no perfect method to model stellar activity, but what we know is that now our methods are very complementary. And the most complementary part is, are you able to model the long time cycle-induced variations or the quasi-periodic variations induced by activity? A last point to just say that, yeah, I haven't talked about supergranulation, and I just want to shout out to Niamh O'Sullivan, who is a PhD student at the University of Oxford with Suzanne, that is working on this topic, and this topic is really being more and more tackled in the community. Yeah, on this word, I will stop here and be very happy to answer questions.
Awesome. Thank you for a very excellent talk, Baptiste. We'll handle questions by having folks raise their hands in Zoom, and then I'll call on you, and you can unmute and ask. Before we jump into that, just because I see some names on our participants list that I don't think are on the RCN mailing list, I'm going to pop a link into the Zoom chat that has the Google form to sign up to join the RCN. Visitors are welcome, so you don't need to join, but if you do, you'll be added to the mailing list, so you'll get updates about future colloquia and other events that we're holding. It'll also get you access to the RCN Google Drive, where we have a full presentation archive of all of the previous colloquia and seminars that we've had, and so you'll be able to access those videos if they're of interest. Okay, so feel free to click that. The form should take less than 30 seconds to fill out. It's pretty brief. Okay, I see a question from Jan in the chat, so why don't we start there? She says, great talk. I have a follow-up question about the planet injection tests. Do you have any intuition about why the 10 to 40-day signals are all systematically bad? I would naively have thought that the 14 to 15-day and 25 to 30-day are quite difficult to recover, but 15 to 25 days are still quite different from the solar rotation period. You're muted, Baptiste.
Thank you. I don't know, I got muted. Okay, thank you for asking. Yeah, that's a fair point. I would say that from my experience with modeling the sun with Gaussian processes, we do get quite a lot of power in the first harmonic of the solar rotation period. So within like 13 to 15 days, you will lose your planet because of this first harmonic. Then, yeah, between 15 and 27, you're probably sensitive still, like our Doppler imaging, since we are working on only one rotation period chunk, you're probably quite sensitive to effects that are on the same order of magnitude of the rotation period of the sun. I would say that's probably the main reason.
Hey, Jan says, thanks for the answer. Other questions for Baptiste, feel free to raise your hand via Zoom. Andrew, go right ahead.
Hi, Baptiste. Great talk. Thank you. I applaud your efforts to model the planetary motion simultaneously with the Doppler imaging. And I think that is also true of scalpels and DCPCA and everything else. I think Michael is here. I hope I'm not giving any secrets away, because you can see it with the naked eye when you plot out the radial velocity curves. But since he's injecting planets into the same solar data set that you've been using, there is one of his challenge things for the PLATO exercise where there is something that appears to have an orbital period very comparable to the solar cycle period. And when you look at the scalpel's basis vectors that model the activity, one of them tracks the solar cycle, and its coefficient is horribly distorted by crosstalk with that planet. So as soon as you've got planets in your data set that have an amplitude bigger than the activity, there is a massive danger of crosstalk, and you have to, planets are particularly, in the PLATO problem where you have transiting planets. If you've got non-transiting ones as well, then you have a problem, because the non-transiting ones are another source of correlated noise. So anyway, I think you're heading in absolutely the right direction there, and I'm very glad to hear it. But yeah, these are really impressive results. Congratulations.
I fully agree. I remember when on DCPCA, and this is the same at Scalpel, if we definitely don't include the planet search in simultaneously to activity filtering, we are most likely to lose these larger planets because, of this crosstalk effect you were mentioning. Indeed, that's tough.
And I think, I think, Anciana John did a great job in her papers of making sure that simultaneous modeling was done, and it makes a huge difference if you want to measure the mass of a transiting planet.
Absolutely, yeah, I agree.
Yeah, thanks.
Other questions from the audience? I'll ask one while people ponder. So Baptiste, sorry if you mentioned this and I missed it. Can you talk a little bit about the scope or the scale of data that is necessary to do this type of work if we were to try and do this on other stars down the line and we don't have 8 years of beautiful every single day observations?
Yeah, that's a fair question. I don't know. It was hard to assess. So we are definitely sampling dependent. So, you know, at least you can, what I showed is that you can apply Doppler imaging on any, if you have enough data to cover one rotation period, then you can apply Doppler imaging independently on each rotation period, at least using traditional method. The test I made is I said, okay, what's the dependency or ability to match the injected map? So what you see, the color code here is the correlation between an injected map and the map recovered with Doppler imaging as a function of the noise in the CCF and as a function of the number of points. Well, I mean, 0.03% is typically the noise level. I mean, it's typically when the noise level overshadows the activity-induced signature. So definitely you don't want to go there. But as long as you get sufficiently precise spectra, that's really what the most important is. And you need typically around 10 points per rotation period. And you see that, yeah, basically you really perform very badly when you have not enough points because you end up with big gaps in your stellar surface. But then if you increase and you typically go on this sweet spot, that's a decently good match, I would say. So in the end, yeah, not too dramatically dependent on, I mean, to an extent.
Yeah, that's very encouraging. Thank you. Tom Laredo, I see your hand up. Go right ahead.
Hi, that was a great talk. Thanks so much. Just a little detail question. When you get when you use the chunk data and get the planet parameters separately for each chunk, how do you combine those to get a final overall estimate?
Yeah, so I definitely work chunk by chunk until I can get an estimate of, so for each chunk, I will get an estimate on error bars for the local, for example, semi-amplitude of the planet. And afterwards, only I will combine these so that I don't want to combine chi-square maps beforehand. That would probably be a bit harder to quantify the degrees of freedom. So that's the way I will do that. Then for each chunk, yeah, I'm doing that for each chunk. Sometimes I don't get a very precise value for KP, but overall what I noticed is that you get a decent estimate accuracy on your semi-amplitude, but sometimes you do get super larger error bar, like 0.4 meter per second. But these are cannot absorbed when I will combine all my KPs in the end. So something I wanted to check that I haven't done yet is checking which chunk will get us the most precise estimates on KP. Is it just because you have more points, or is it because of activity is better captured? That really things that I want to investigate for the paper as well. I don't know if I answered kind of your question.
I think so. So you're basically using propagation of errors just for each parameter. Got it. Okay.
Exactly. That's you know, that's the way I was like, I felt the most comfy doing this way. I didn't want to jinx it.
I get it. Thank you.
I like the prioritization of comfiness in science.
Yeah, fair.
Okay, any other questions for Baptiste from the audience? Okay, if not, why don't we thank Baptiste again for a wonderful presentation. Thank you so much to everybody for calling in for today's colloquium. And again, we will be back next month with Sam Thompson talking about HARPS-3 and the Terra HuntingExperiment. So looking forward to see many of you online then. Have a great month in the meantime, everybody. Catch you in March.